Okay. Good morning to all of you.
Good
Before
morning,
we
ma'am.
start, let me present the screen. Presentation is visible, right?
No, ma'am.
Now? Now it is visible?
No,
No,
ma'am.
ma'am.
It's not visible.
I started sharing.
But it's not visible, ma'am.
1 second. Now can you see this?
No, ma'am.
I'm trying to share it as a window. You can click on that presentation if that icon is visible to you.
No, ma'am. It's not visible. Yes, ma'am. Now it's visible.
Visible? Okay, fine.
Yes, ma'am.
Right? It's visible, right?
Yes, ma'am. Visible.
Okay, fine, fine. Okay, welcome to this third lecture under module 4. In last few sessions, we have seen HDFS concepts like blocks, name nodes and data nodes, how they work in master worker pattern, and HDFS federation, how it enables to scale the capacity of name nodes so that each name node can take care of files routed under a particular route, and HDFS and HDFS high availability, how it is ensured by using active standby name node configuration, and also failover and fencing, how these two features help to ensure that at one point of time only one name node will be active and working. And also we have seen how to work from command line interface in order to interact with HDFS. In that we have seen setting of two properties. One is the file system property, name of the default file system, and the other one is to set the replication factor. We have seen how to set up a single machine in a pseudo distributed mode and work with HDFS. In today's lecture, we are going to cover about basic file system operations and Hadoop file systems, and also interfaces like HTTP, C, and Fuse. Now, let us see some basic file system operations first. The file system is actually ready to be used. You need not configure it much. The file system is ready to be used, and we can do all of the usual file system operations like reading the files, creating the directories, moving the files from one location to another location, deleting the data, and listing the data. To know detailed information about this, you can type this command Hadoop Filesystem -help, which can be used to get detailed help on every command. Now let us do a small function of copying a local file to HDFS cluster and HDFS a file on HDFS cluster back to a local disk, right? Let us do this small operation to understand how it actually works. Now start by copying a file from the local file system to HDFS. How do you do that? I already told that all the Hadoop instructions start with a percentage symbol, percentage Hadoop. Now you give the file system tool here, fs hyphen copy from local. This is the command used to copy a file from local disk to HDFS cluster. So you're using hyphen copy from local command, and you're copying it to this path on HDFS cluster, onto a HDFS node. That is by using a path, for example, input docs The file you're actually copying is quangle.txt here. Okay. Now you're using HDFS URI in order to make the local host itself as HDFS, because you're working in a pseudo distributed mode. Now your HDFS is also on the local system. That is why you're using HDFS localhost and using the path user Tom and copying this quangle.txt into this particular file, right? So you're copying from the local disk location to your HDFS cluster. Because you're working in a pseudo distributed mode, your HDFS cluster is also on the local host. That is why you're using the URI like this, HDFS localhost. Now, what is the first, another alternative for this kind of copying a file? We can omit the scheme and host of the URI, that is this part. We can omit this part and pick up the default so that this part can be omitted and the command can be rewritten as %Hadoop from the file system, copy from local disk, locate the file from the local disk and copy it onto the HDFS cluster. This is the path to find your file on the local disk, and this is the path to copy it onto your HDFS cluster. Because you have taken the URI scheme as HDFS localhost, you can try to omit this and directly pick up the pick it up like a default. And other alternative is we can also use a relative path and copy the file to our home directory in HDFS. Remember, we are working in a pseudo distributed mode again. That is why you need not actually mention the path, because you're working in a home directory. You can directly give the command like this: %Hadoop fs copy from local, give the local disk address and onto which file you're copying in your home directory in HDFS. That is why you have even omitted this part. That is because that is your working directory, home directory. That is why you omitted that and directly you gave the file name into which it has to be copied onto your HDFS cluster. Right? Now, let us copy the file back from HDFS cluster to the local file system once again. This is just to get used to how to perform the basic file system operations, right? That is why after copying the file from local disk to HDFS cluster, now we are trying to give a command to copy a file from HDFS cluster back to its local disk, back to its local file system, and check whether it is the same. Let us also perform a check whether the file is copied intact without losing any data integrity, without causing any disturbance to the data in the file. Right? First, let us see how to copy it back to the local disk. We are giving Hadoop file system copy to local. If you want to copy a file from local disk to HDFS cluster, you are using copy from local. But here you are copying a file from HDFS cluster back to your local disk, back to your local file system. That is why you are using copy to local, from which file on HDFS cluster you are copying, quangle.txt, and you're creating another copy on your local disk just to see whether both the files are matching or not. You're creating a copy of it on the local disk, right? Now you're performing a message, you're executing a message digest algorithm on this file that is copied and the copy that is created in your local disk, and seeing whether they're giving the same hash key or not. This MD5 is a message digest algorithm which generates 128-bit hash keys in order to see whether the data is intact or not, the data is consistent or not after transferring the file to and fro. For that, we have used this message digest algorithm on this quangle.txt, the original file copied from HDFS to the original file copied from local disk to HDFS, and a copy of it created after copying it from HDFS cluster back to your local file, right? When we compare these two hash keys, both are the same. This indicates that the file is copied safely onto HDFS cluster and back to the local disk without causing any disturbance to the data in that file. Right? Now finally, let us look at an HDFS file list. Any doubt?
Yes, ma'am, I have one doubt. Can you
Yeah, please tell me.
Ma'am, here you have used this basic file system operation. So the
Okay.
first one you are saying that you are copying from Hadoop to local. So you have
No.
used the name.
First command is to copy from your local disk file, local file system to HDFS cluster.
Yes, ma'am. Local file system to HDFS.
To
So you are
HDFS cluster.
using that quaggle.copy.txt. So, ma'am, if we will not use dot copy, then will it work?
This is no your previous command. This command is to copy from local disk to your HDFS cluster. That is why you're using copy from local. Now
Okay,
you're
ma'am.
copying it from HDFS cluster to your local disk by using copy to local command. Tell me
So, ma'am, this dot copy is the command or this is the file name?
which one?
This quaggle.copy.txt.
Quaggle.copy.text, you're creating a copy of the original file. Why? Because there is already original file with quaggle.text, right? Which is copied from your local disk to HDFS cluster. Now, once
So,
again,
ma'am,
you wanted to check whether you're able to copy it back to local disk safely or not. For that purpose, you're not working with the original file, but you're creating a copy and copying the file into this copy.
so, ma'am, it's a command now. It is a
No,
command.
it is the file name. It is not a
It is
command.
a file. You can use anything in place of that.
You can use any name. You can use abc.copy.text also. Or you can
So,
use
ma'am,
entirely different name, pqr.text. Your original file is abc.text. Now you can create a copy of it by using pqr.text.
okay, ma'am, that is me.
Right? And this is
Yes,
how
ma'am.
you're creating, you're finding its intactness. You're finding its
Okay,
consistency by implementing a message digest algorithm. Right?
okay. Yes, ma'am, right.
Okay. Now finally, let's look at an HDFS file listing. Now, if you want to create a directory first, just to see how it is displayed in the listing, whenever you just list out all the files in the directory and all the directories also, how it actually presents. If you want to see that, let us create a directory first. Percentage Hadoop file system. In this file system, you're creating a directory, you're making a directory by using -mkdir, and you're creating a directory by the name books. Okay, now you're displaying all the directories and files in this file system by using ls command. You know this command, right? It's a Unix command in order to list all the components of a particular file system, right? So this is how the entire file system contents are listed out. So how to understand this representation? These are the modes in which the file is open. Means whether it is in a read mode or write mode, or if it is an append mode, those modes can be presented here. And see this part, the second column. This indicates the replication factor. For directories, you can't replicate it. You need not actually store any copy of the directories. That is why the replication factor is nil here. But in this case, for this quangle.text, the replication factor is 1. Remember, again, I am stressing on this. You are working in a pseudo distributed mode. That is why you have set the property from your command line interface, the replication factor to be 1, because you can't create multiple copies because you're working on only one single machine. That is why it is representing the replication factor as 1. And this is the owner of the file, name of the owner of the file, and the group to which he belongs, admin, supergroup, or a group, right? And this part, this column indicates the file size in terms of bytes. Because this is a directory, books is a directory you have created here, it is not occupying any bytes. But quangle.text here, it is occupying 118 bytes. And the next column indicates the last modified date and time of the file. recently modified date and time of the file or the directory, right? And this final column indicates the absolute path to the directory or to the file. Did you understand this representation?
Yes, ma'am.
Okay. Now let us see about Hadoop file systems. Hadoop has an abstract notion of file system, of which HDFS is just one implementation. We have various such implementations of Hadoop file system. The Java abstract class org Apache Hadoop is the abstract class from which you can implement various from which you can have various concrete implementation. This represents a file system in Hadoop, and there are several concrete implementations which are described in the following table. Now we are going to see various other concrete implementations of this Hadoop file system. Okay, the first file system we can discuss about is local file system, and its URI scheme means how you specify the URI scheme is simply a file. Now the Java implementation, remember all these are under org Apache Hadoop. So whenever you write this, you have to write it as org Apache Hadoop .fs .local file system. Right? What does this file system, local file system indicate? It is a file system for a locally connected disk with client-side checksums. Client-side checksums in the sense, why checksums are used actually? Checksums are used to see whether the data is consistent after reading or writing or transferring the data from one disk to another disk, from one file system to another file system, whether the data is consistent, whether the data integrity is retained or not. That is checked by using these checksums. Okay, for this local file system, these checksums are available on the client side itself. But if you don't want to implement those checksums, in that case, you can use raw local file system for a local file system with no checksums, with no checksum facility, right? And the second file system is HDFS. We have seen this already, and the URI scheme for this is HDFS. HDFS can be used as HDFS dot distributed file system. This is Hadoop's distributed file system, and it is designed to work efficiently in combination with MapReduce, in conjunction with MapReduce, because MapReduce jobs try to read data on this Hadoop distributed file system, right? So this HDFS and MapReduce work together. Next type of file system is HFTP. Remember, this doesn't have any connection with FTP. It is just HFTP, which is implemented over HTTP. A file system providing read-only access to HDFS over HTTP, right? And often it is used with dist CP, which we are going to see in the last part of this chapter. And it is used to copy data between HDFS clusters running different versions. When HDFS clusters are running different versions, in order to transfer data, in order to copy data between different clusters, we use this HFTP, which helps us to access HDFS over hypertext transfer protocol. And the same type of file system is HSFTP, which actually works on more secure mode. In the sense, a file system providing read-only access to HDFS over HTTPS, over secure HTTP, right? That is the only difference. Next type of file system is Web HDFS, and the URI that is used, hdfs.web.webhdfs file system, and this is a file system providing secure read-write access to HDFS over HTTP, and Web HDFS is intended as a replacement for HFTP and HSFTP. Why? Because HSFTP and HFTP, they only support read, means read only is allowed in these two file systems. That is why another modified version have been introduced, that is Web HDFS, which also provides read-write access as well as some Kerberos authentication facility also, which helps to establish secure communication between the users for communicating over insecure connections. Now the next file system is HAR, which is also called as Hadoop Archive. This uses fs.har file system, a file system layered on another file system for archiving the files. Hadoop archives are typically used for archiving files in HDFS in order to reduce the name nodes memory usage, because you can't keep all the files readily available on data nodes all the time. Say if there are infrequently accessed files, you can't simply waste the space on data nodes and further wastage of space of storing the metadata on name nodes. You can just archive them. So Hadoop archives are typically used for archiving files in HDFS to reduce name nodes memory usage. And the next type of file system is KFS over Cloud Store. This uses the URI KFS with Cosmos file system. This cloud store, formerly it was called as Cosmos file system, is a distributed file system like HDFS for Google file system, and it is written in C++. If you want to dig in depth on this, you can use this URL and check the information. And next type of file system is FTP. This uses this URI fs.ftp file system, and this is a file system backed by an FTP server, the simplest server, file transfer protocol server. And the next type of file system is S3 native, and the URI used is fs.s3 native S3 file system. And this is a file system backed by Amazon Simple Storage Service. S3 stands for Simple Storage Service. This helps to perform object storage by using web service interfaces, right? And the next one is also the same, S3, but it is block based. In the previous case, it is native file system, but in advanced version, it is block based, where it uses fs.s3.s3 file system. And this file system is also backed by Amazon S3, which stores files in the form of blocks. Means the block abstraction used in the previous case is files, but in this case it is blocks. And this helps to overcome the drawback of normal native S3, where the file size limitation is only 5 gigabytes. But in this case, because you're storing the data in the form of blocks, you just need to see the storage mechanism in the form of blocks and just calculate how many blocks can be accommodated for a particular disk or for a particular node. You need not see how many files will be accommodated. You can just split it into blocks and see how many blocks can be accommodated. And next type is distributed RAID. I already spoke about this RAID mechanism. It is redundant array of inexpensive or independent disks, which help us to store the data by storing replicated data, by storing duplicate data, providing data security to overcome data loss or data corruption. Okay, in this distributed RAID, we use the scheme as HDFS dot distributed RAID file system. Now, a RAID version of HDFS designed for archival storage. This is mainly used for archival storage. For each file in HDFS, a smaller parity file is created, which allows the HDFS replication to be reduced 3 to 2, which reduces the disk usage also by 25% to 30%. While keeping the probability of data loss the same. Though the data loss probability can be reduced, this storage space can be saved by not replicating the entire file as it is, but by creating a parity file out of a file and storing that parity file. Remember, if you want to create a mirror copy of a file, it consumes the same space as the original file. But if you create a parity file, it almost uses only 25% of the original file. Parity is like performing some operation, which gives us some result, which can be compared with the original file's calculation. right? So creating a parity file will reduce the memory usage from 25 to 30%, though it can't improve the data probability of data loss. Reduce the probability of data loss. This distributed RAID requires that you run a RAID node daemon on the cluster. But when you are implementing this distributed RAID, you have to run one extra daemon on HDFS cluster, that is RAID node daemon. Normally, Hadoop uses 5 daemons to perform its task. One is the name node, and next secondary name node, and then data node, and job tracker and task tracker, which we are going to see in later modules. These are the 5 daemons used by HDFS to perform the data storage and analysis process. In addition to this, if you are implementing this distributed RAID file system, then it has to use another daemon called as RAID node daemon, which has to be run on the cluster. And the last type of file system is view, which is indicated as viewfs.view file system. This is a client-side mount table for Hadoop file systems and commonly used to create mount points for federated name nodes. When you are scaling up the name node capacity, when you are adding multiple name nodes, it is used to create mount points for these federated name nodes, right? Now, Hadoop provides many interfaces to its file systems, and it generally uses the URI scheme to pick the exact file system instance to communicate with. There are lots of implementations here, what I have shown in the previous slides. And this Hadoop uses the URI scheme to pick up the correct file system instance in order to communicate with that file system. Although it is impossible to run MapReduce programs that access any of these file systems, when you are processing large volumes of data, you should choose a distributed file system that has the data locality optimization, notably HDFS. Means when you are choosing a distributed file system, you have to choose the most optimized file system, which is very close to the very close to your MapReduce jobs, so that you can reduce the time spent on locating that particular data. Why? Because the data is locally situated. We are actually highlighting the feature of data locality here. We're trying to optimize the locality of the data in order to save on time spent on locating that data on the data nodes. Now let us see some interfaces written for Hadoop. Hadoop is normally written in Java, and all Hadoop file system interactions are mediated through the Java APIs, through the Java application programming interfaces. The file system shell, for example, is a Java application that uses the Java file system class to provide file system operations. So the class that you need to use is the Java file system class in order to provide the file system operations. Now, let us see about the HTTP interface. There are 2 ways of accessing HDFS if you are accessing it over HTTP. One is directly, where the HDFS daemons serve HTTP requests to clients. Means there is no mediator in this case. The HDFS daemons directly serve the HTTP request to clients. But the second mechanism is to have a proxy which accesses HDFS on the client's behalf using the usual distributed file system API. Means there is a mediator in this case which acts as a proxy which communicates on behalf of the client with HDFS. Now this is how it is depicted in this figure. In the first case, here the client is directly interacting with the name nodes and the data nodes. Name nodes will serve with the directory listings, whereas the data nodes will serve with the streaming data to the clients directly. But in the next case, again in this direct access, HTTP uses HFTP and HSFTP also, and sometimes it uses Web FTP also. This Web FTP provides extra features like Kerberos authentication. That is why this name nodes and data nodes services are provided through an embedded web server, which uses this web FTP in order to communicate with the clients. And in the next case, it is using a mediator, HDFS proxy. Means HDFS proxy will communicate with the name nodes and data nodes on behalf of the client. This is actually useful in cases where you want to set up extra firewalls and also some bandwidth optimization policies if you want to introduce or implement some extra security mechanisms like firewalls. In such case, implementing HDFS proxy is always an advantage. And this HDFS proxy also helps to copy the data across various clusters where, in different data centers, clusters residing on in different data centers. You can see here this solid line indicates HTTP request and the dotted line indicates a remote processor request, and little thick dotted line indicates the block request. Means it indicates that not only within the data center but across the data centers, between various clusters also the data can be transferred using HDFS proxies. And there is another interface written in C, and Hadoop provides a C library called libHDFS that mirrors the Java file system interface. It is same as Java file system interface. It works using the Java native interface to call a Java file system client. It uses JNI to call the Java file system client. You can find the generated documentation for the C API in this directory if you want to go through library HDFS /docs/API directory. If you go to this directory, you can find generated documentation for this C API. And the last interface that we are going to discuss is file system in user space, which is in short called as Fuse. It allows file systems that are implemented in user space to be integrated as a Unix file system. Means this gives you the experience of working with Unix file system. And Hadoop's Fuse distributed file system contrib module allows any Hadoop file system, but typically HDFS is used to be mounted as a standard file system. And we can then use Unix utilities like ls, listing the file system components, and cat to interact with the file system. And POSIX libraries, portable operating system interface libraries, can be used to access the file system from any programming language. You don't have any restriction about the programming language. You can use this POSIX libraries to access the file system from any type of programming languages you're working with. And Fuse DFS is implemented in C using library HDFS as the interface to this HDFS cluster, right? These are the interfaces which you have to just remember. I think these are not very important, but you need to know what are the interfaces available in order to interact with the HDFS clusters. Okay, in next lecture, we are going to see about the Java interface and how to write programs to read data from a Hadoop URL and read data using file system API as an alternative, and what is the significance of FS data input stream and how to write data to the file by using the Java interface, and how FS data output stream is used, and also directories. Any doubts so far to be discussed?
No, ma'am.
Okay, it's very clear. Concepts are very clear.
Yes, ma'am.
Because we don't have this big data analytics lab, we can't implement these commands. But if you have a basic idea about how to work with this, so when you're working with this in industry, you will just memorize. It will ring the bell for you that I have learned about this concept. So you have the basic idea. You can quickly cope up with the other commands when you come across, right? Okay. Shall we end the meeting then?
Yes, ma'am.
Okay. Thank you. We'll meet in the next lecture.